Assalamualaikum and good day to all of you. So this is my video for chapter 2, AC or alternating current for single phase circuit. Okay, these are the contents for chapter 2. So in this chapter, it will be divided into 4 parts. So for part 1, we will learn about the introduction, AC in resistive circuit, AC in inductive circuit, AC in capacitive circuit, AC in series, and then effect of frequency variance. Okay, so for part B, we are going to learn about AC parallel RLC circuit, power in RLC loads, apparent power, relationship between P, Q, and S, power factor, and power factor correction. Okay, so, and then for part C and D, we will cover measurement of power and resonance in AC circuit. So each part, I will make a video for 4 weeks. So week 1 is part A, week 2 is part B, week 3 is part C, and week 4 is part D. Okay, so let's continue with part A. So these are the objectives for this chapter. So the first one is you can calculate inductive and capacitive reactance, draw the phasor diagram, voltage and current waveform, draw the phasor diagram of RL, RC, RLC in series and parallel circuit, and also calculate P, Q, and S to the load, construct a power triangle and analyze the complex number and also complex load, calculate power factor, explain why equipment is rated in VA instead of watts, measure power in single phase circuit, determine resonance frequency on simple series and parallel circuit, and find quality factor Q of a resonance circuit. Okay, so for part 1, okay, so this is the introduction of this part. So this chapter are related to circuit theory 1 and also engineering maths. So you will apply Ohm's law, Kirchhoff law, current divider, current voltage divider, and also how you want to express AC voltage and current in terms of time domain or function of time, and also frequency domain or phasor. So last week in chapter 1, we have learned 3 terms about relationship between two waveforms, either in phase, lead, and lag. Okay, so this is the connection how we want to differentiate between single phase and 3 phase at TNB metering. So these are the schematic diagram, or these are the system, power system in generating AC supply. So this is the first part is generating station, and then transmission station, and the last one is distribution station. Okay, so for chapter 2, we will learn about single phase, and then for chapter 3, we will learn about 3 phase. So this is the basic AC circuit, which include voltage supply and load that is connected via the electric wire. So the load is either R, L, or C, or combination of R, L, and C. Okay, so second subtopic is AC in resistive load. So where the circuit only have resistive as your load. So this is your supply, power supply, and then this is your load, where your load is a resistor. Okay, so as you know, Ohm's law state that current is directly proportional to voltage. So you apply Ohm's law, V equal to IR. So this is the proof step how you want to get the expression I equal to Im is I maximum sine omega t. So notice that there is no phase difference because voltage and current are in phase. So this is the waveform of voltage and current for purely resistive circuit where your voltage and current are in phase. So this is how we draw phasor diagram. So your voltage and current is at x-axis because your phase difference is 0. Okay, so this is the example of AC for purely resistive circuit. So given R equal to 5 ohm and your expression of pi is 12 sine omega t minus 18 degree. So determine VR and draw the waveform. So apply Ohm's law. So V equal to IR. So you will get 12 times 5 sine omega t minus 18. So your V is 60 sine omega t minus 18 degree. So this is how you draw the waveform. So why your waveform is shifted to the right? Because of this value, this negative value. So negative 18. So what we have learned in chapter 1, if the value of your degree is negative, so your waveform is shifted to the right of your y-axis. So both voltage and current is starting at the same point where your phase difference is 18 degree. Okay, so for voltage, your maximum voltage is 60, and then for current, your maximum current is 12. Okay, AC in inductive circuit. Okay, so ideal inductor attribute VL is proportional to the rate of change of current. So mathematically, this is the formula. So VL equal to L di over dt. So finally, you will get VL equal to omega L I maximum cos omega t. And then V equal to, you apply Ohm's law, then you will get VL equal to Vm cos omega t. So since omega or angular velocity is equal to 2 pi f and cos x equal to sine x plus 90, this is mathematical approach solution. So finally you will get VL equal to Vm sine omega t plus 90 degree. And then IL equal to Im sine omega t. So this is how they prove this expression. So where Vm equal to 2 pi FL Im. So you just rearrange this formula, then you will get this one. So unit for inductive reactance is ohm. Okay, Okay, so from the proven step, so we can say that inductive reactance SL. So please remember SL is inductive reactance. So inductive reactance is equal to 2 pi FL, or inductive reactance is also same or equal to omega F. So this is the graph for the relationship between SL and current. Okay, so here are the waveform of voltage and current in purely inductive circuit. So where your V is lead, or V is leading I. So remember we have learned CI-VIL. So for inductive, so draw first. So CI-VIL. So for inductive load, your V is leading I. So that's why you get this waveform. So V is leading I. So how we are going to draw the phasor diagram? So V is leading I with 90 degrees phase difference, or I lag V by 90 degrees. Okay, so let's try this example. Okay, you have VL is 100 sine 400t plus 70 degree. So determine IL and sketch the phasor diagram and waveform. So first of all, you have to identify the expression. So 100 is your VM, and then this is your omega. So from the expression, you can identify what is your VM value and what is your omega. So from here we can see that your omega is 400 radian per second. So therefore, so SL equal to omega L. So you have the information of omega, where is 400, and your L is 0.2. So therefore, your inductive reactance is 80 ohm. Okay. And then using Ohm's law, so IM equal to VM over SL. So VM is 100 divided by SL 80, you will get 1.25. So let's draw the, okay, then the question asks you determine IL. So IL equal to, refer to the formula before, IL equal to Im sine omega t plus or minus theta. So since we know that the current lag voltage by 90, so you just minus 70 minus 90, so that's why you will get negative 20. So this is how you draw the waveform. So voltage is leading current, and then you just determine where is your VM, where is your IN, and then your phase difference. So okay, so from here we can draw the phasor diagram. So VL is leading IL by 70 degree. So this one, sorry, VL is leading IL by 90 degree. So here is 70 and then you plus 20. So you get 90 degree. Okay, and then next subtopic is AC in capacitive circuit. So this is the connection of circuit where we have purely resistive load. So you have supply here and then capacitor will be your load. So IC is proportional to the rate of change of voltage. So IC equal to C dV of C over dt. So this is mathematical solution. How we will get IC equal to Im cos omega t, or IC equal to omega C Vm cos omega t. So apply the same concept as in inductive circuit. So you will get Vc equal to Vm sin omega t, and then Ic equal to Im sin omega t plus 90. So this one just use Ohm's law. So Vm over Im equal to 1 over 2 pi Fc. Okay, so therefore you will get Hc is equal to 1 over 2 pi Fc. So this one we call capacitive reactance. Okay, so this formula you have to remember. So Hc equal to 1 over 2 pi Fc. So this is the relationship between Hc and supply frequency. And then, so from this graph, we can say that Hc is inversely proportional to supply frequency. So you can see inversely proportional. So the higher the frequency, the lower of your Hc value. While for a given voltage, current produced is proportional to the frequency. So you can see the higher your frequency, your current also increase. So this is the waveform of voltage and current in capacitive. So you can see here, current is lead voltage. Okay, so this is the phasor diagram. So current lead voltage by 90 degree. This other example where your VC, this one is VC at 0, and then this one VC at negative 30. So where your value of angle between x-axis for IC is 60. So 60 plus 30 is 90 degree. Okay, so let's try this example. So same step as for inductive load. So where you have to identify your omega value and then your Im. So this is your Im. So therefore, Hc equal to 1 over omega c. So you will get 10 kilo ohm. And then using Ohm's law, Vm equal to Im at C. So Vm you will get 50 ohm. So as we know, the voltage lag current by 90 degree. So therefore, you just minus 120 because this one is in current, so you have to minus 90 degree. So you will get 30 degree. So this is how you draw your phasor diagram and your waveform. Okay, so these are the conclusion from three types of load, where you have purely resistive, pure inductive load, and pure capacitive load. So other than civil, you also can remember using these terms. So Ellie the husband. So for inductor, your E is actually for voltage. So E lead I. And then for capacitor, I lead V. So either one you want to remember using civil term or Ellie the Iceman. Okay, and then we go to next subtopic is AC in series. So this is the connection of AC in series or series circuit. So and then this is the connection for parallel circuit. Okay, so first we look into R and L in series, where you have the combination between resistor and inductor in series. So apply KVL. So where we supply plus we supply equal to VR plus VL, or negative V supply plus VR plus VL equal to 0. So you know that VL equal to IXL and VR equal to IR. So this is the phasor diagram. So your VR is here at x-axis, and then your VL is positive. So this is your total V. Using vector representative. So how you want to get the value of V? So using theorem Pythagoras, so this is your hypotenuse. So you will get this formula. Or you can read using Ohm's law. So that's why you will get this formula. Okay. And then you rearrange becomes this formula. So finally you will get V equal to Iz. So what is your Z? So Z is equal to square root of R square plus XL square. So Z is your impedance or galangan. Okay, so Z is impedance of your system as Z equal to R plus J XL. J is your complex number. So in electrical, instead we use J. So in maths you use I, right, for your imaginary part, but in electrical we use J. So if you want to find the magnitude of your impedance, so magnitude of impedance equal to square root of R square plus XL square. So the relationship between impedance and voltage phasor. So your VR is at axis because your theta is 0. So VR is positive, and then you will get V is here. So and then we can draw impedance triangle. So your R is at axis, as L is in positive, then you will get Z here. That's why your formula for Z is this one, where you find the hypotenuse from this impedance triangle. Okay, so how you want to find the theta? So apply theorem Pythagoras. So theta equal to inverse tangent VL over VR, or if you use impedance triangle, so theta equal to inverse of tangent SL over R, or theta equal to inverse of cosine R over Z. This one just apply theorem Pythagoras. Okay, so let's see the example. Reactance, okay, find the reactance and impedance. So what is the difference between reactance and impedance? Okay, so your reactance is SL, and then your impedance is your Z. Okay, so first of all, you have to find your SL. So SL equal to okay, so J, so omega is what is the formula for omega for angular velocity? So omega equal to 2 pi f. So 2 pi f. Okay, so omega equal to 2 pi. So your f is 50. So you will get 2 pi times 50 is 314.16. So radian per second. So 314.16 times your L is 100 milli. So you will get J 31.42. So what is your impedance? So impedance equal to R plus SL. So equal to 12 plus J 31.42. Okay, so this one for A. Okay, for B, current. The current. So just apply Ohm's law. V equal to IZ. So your I equal to your V is 100. So we assume V as your reference. Sorry, theta 0, and then divide by 12 plus J 31.42. So using calculator and complex number, So 100 divided by 12 plus 31.42 I. Okay. So you will get 1.06 minus J 2.78 M, or you can change to polar form. You will get 2.97. Your degree is negative 69 degree. So this is your answer. Okay. And then the last one, phase difference between current and voltage. So now you can see why I change this complex number into polar form, because I want to know the degree. So the phase difference between voltage supply. So this is your voltage supply and this is your current. So the phase difference between voltage supply and current is 96 degree. So this is the answer. Okay, so for exercise 1 and 2, I want you to try by yourself and then share your answer during our next class. Okay, and then R and C in series. So I skip for the proven step. So you just apply the same step as R and L in series. So your V is at x-axis, and then your X at C is in negative value. So that's why your at C is going down. So you will get your V is here. So V equal to, so apply the same concept. So V equal to Iz, where your impedance is Z equal to R minus J at C. So Z equal to square root of R square plus at C square. So this is how you draw the impedance. So this is your R at x-axis and your XC is going down. So this is your Z. So apply theorem Pythagoras and then you will get your theta. Okay, so using all this formula, so please try this example and then we are going to discuss this example in next class. Okay, the last one for series circuit is combination of R, L, and C in series circuit. So apply KVL. So you will get this equation. So this is how you draw the phasor diagram. Your VR is at x-axis. So this is VL minus VC or SL minus XC. So this is your V, or if you use XL minus XC, so this is your Z. Okay, this is so if VC is larger than VL, your triangle will become like this. So finally, your Z is equal to R plus J XL minus XC. So, and then your magnitude of or your total impedance is square root of R square plus omega L minus 1 over omega C square. So this is your impedance triangle. So from impedance triangle, you can find your theta. Okay. So for this example also, I want you to try. So any question we can discuss in our next class. Okay. So effect final subtopic for part A is effect of frequency variation. So variation of inductance with frequency. So you know that SL equal to omega L, where omega equal to 2 pi f L. So this is your frequency and this is your inductance. Okay, so SL is your inductive reactance. So from this formula, if frequency is double, your F is double, your reactance also double. And then if your frequency is half, your reactance also half, and so on. Okay. But if the inductance, so this is your inductance, is double, so your reactance also double. So if your inductance is half, your reactance also half. So from this formula, we can draw or we can get this type of graph. So you, for example, so from this statement, we can say that inductance is proportional to frequency. Inductance reactance is directly proportional to frequency and inductance. Okay, so apply this formula. So a circuit have 50 ohms inductive reactance. So if both inductance and the frequency are double, so what is your new? So inductance double and frequency double. So you have, in order to find new SL, you have to times by 4 because of inductance double and frequency double. So that's why you will get the new SL is 200. So okay, so now we look into variation of capacitive reactance with frequency. So before this, variation of inductive reactance. Now capacitive reactance. So from this formula, Xc is equal to 1 over omega C or 1 over 2 pi Fl. So we can say that capacitive reactance is inversely proportional with frequency because 1 over 2 pi Fc. So the higher the frequency, the lower the reactance. So that's why you will get this curve due to capacitive reactance is inversely proportional. So at frequency 0, you can see here, the capacitive reactance is infinite because your curve is actually like this. So if capacitance is double, reactance half because of this relationship. Okay, and then the last one is variation of impedance of RLC series with frequency. So this is the graph. Okay, so that's all for chapter 2, part A. So next week we will continue our chapter 2 for part B. Thank you.